So this is continuation of our review video for the review sheet for exam 2. Just because the recording reached the maximum limit, I got cut off, and I'm going to continue it as a second part. We were talking about the tonicity of the cells, and tonicity related, of course, to the concept of osmosis, which was one example of passive transport, as we already discussed. So in osmosis, the substances, so in this case these red dots, were not able to cross the membrane, but to get the equal concentration on both sides, it was the water that moved across the membrane. So that was our way to solve it. And we see that in tonicity as hypotonic cells end up having water flowing inside the cell because the insides are more salty, so there's more of these red dots inside the cell, and we try to balance that with the outside by having water coming inside the cell. Water flows inside the cell, and cells end up swelling. And I think that the mnemonic clue that I gave for you, that is was that think of hypos, these animals that are big and swollen. And I'm not the best at drawing hypos. It looks probably more like a pig, but bear with me. So that's our hypocell, big and swollen thing. Well, the next example of tonicity that we discussed were isotonic cells. And I'm again trying to just changed our pen color, highlighter color. I think we finally succeeded to do that. So in isotonic cells, I think that my mnemonic for you was iso-perfect. When you're perfect, you do not have to change. The amount of salts are in balance. So there's no net gain or net loss of water. So the same amount of water enters into the cell as leaves the cell. So overall, the amount of water remains the same. So as a result of that, the cell size remains constant. Cell does not gain size and it does not lose size. And again, I'm just trying to change the color. I think I gave you the mnemonic. Iso-perfect. And if you're perfect, you don't need to change, you remain the same. And the last example of tonicity that we had was the hypertonic cells. Let's have a look of those. So in hypertonic cells, what's happening is that actually the outside of the cell is more salty, so water ends up flowing out from the cell. So in this case, water leaves the cell. And again, you remember this relates to the concept of osmosis. If the outside is more salty, now water is flowing out from the cell. And as water is flowing out from the cell, what we end up noticing is that the cell gets smaller, it shrinks. It can eventually even dry up if the difference is too large. And again, I'm trying to think of what I gave you as mnemonic, I think I told you that think of a person who's hyper. What are people who are hyper? What are they like? They run around a lot, don't they? They have a lot of energy. And what happens if you run around a lot? You become very skinny. So those were our skinny cells. They shrink in size. So that was our hypertonic cells. And we have one more example to go through about passive transport. And that example is going to be our facilitated transport. And I'm just trying to look that I use the same highlighter color. I have a bad tendency of using many colors. So let's have a look of our facilitated transport. What's happening there? In facilitated transport, and again, I'm going to take the same color that we used before. We have substances that are unevenly distributed across the membrane. In this example, all of these substances are on one side. So there's going to be high concentration on this side and low concentration on that side. And these are going to pass the membrane through a protein, and it can't be just any protein. Only specific proteins let specific things to pass through them. But we just accept that these proteins or allow these substances that we have in different concentration to pass, again, from the area of high concentration to the area of low concentration. And the goal is to let these pass until the concentration is the same on both sides of the cell membrane. So they facilitate this passage. No extra energy is spent on it. They simply allow them to go across. Let's remove the 4 that I drew here from this side. And now we have the same amount of substance on both sides. So again, we have reached an equilibrium. So it was indeed let's change the color again. It was indeed these substances that moved across the membrane, but they did it through a specific protein. A certain protein allowed them to pass only. So the protein kind of helped in this process. However, no energy investment. This is still an example of our passive transport, where it's this concentration gradient that was the main driving force. So that's our passive examples of passive transport. And the 2 last examples that I want to discuss about with you are going to be actually examples of active transport. So here, energy is now spent to move substances against their normal concentration gradient. So as you remember, normally substances moved from the area of high concentration to the areas of low concentration. But when we have active transport happening, we often actually move against this gradient and we're moving materials against where they would naturally go. So because of that, because it's not going where they would normally go, we have to invest some energy. We are going against the concentration gradient. And let's have a look at the first example of this. And in this example, what matters is actually these pluses and minuses on these balls. So we'll notice that we have certain ions that are positively charged, so I'm marking all the pluses with red color, and certain ions that are negatively charged, so I'm marking them with blue color. And we have some of each on each side on this diagram. So there's an equilibrium to start with, there's the same amount on both sides. But what happens now is that we take a protein here within the membrane, and this protein allows us to move these ions against where they would normally go to reach this equilibrium where materials from high concentration move to the areas of low concentration. Now we keep moving all of the positively charged molecules, so all of the pluses keep moving to one side, so we can delete them from here. And all of the minuses keep moving to the other side, so we can delete them from this side. And it's thanks to this protein, it moves them to this direction. And because it's not the direction where materials would normally go, of course, this is going to require us to put some energy into that. So this is going to be an example of active transport. And in this case, we talk about movement by using protein pumps. And they establish this difference in charges on two sides of the cell membrane. And you might wonder, why does this matter? When do we do it? And probably the best example of that is a nerve cell. And if you have studied before about nerve cells, often we show them as looking like something like this. They have a nucleus here. They have the cell body with dendrites that collect information from outside world, like little antennas if you wish. They're looking for messages. And then they pass the messages down an axon to the axon terminal, and they might have myelin around the axon. So message would travel one way and one way only. And to do this, the cells, nerve cells, need to have a negative charge inside them, because the electrical message that travels within the nerve cell is actually going to be charge chains. It's a short temporary chains in the inside charge of the nerve cell. Inside of the nerve cell is normally negative 70 millivolts in charge, and when the message travels through, it all of a sudden jumps positive for just that part where the message is traveling. So that's why we need to have active transport in certain cells to generate this charge difference on two sides, so that these cells can do whatever they need to do. You don't need to worry about the nerve cell neuron. That's just in case you're wondering, why on heck would we have protein pumps? Why does it matter? To give a little bit of insight to that. And the last example of active transportation that we're going to see is going to be bulk transport. What happens in bulk transport is that we either have a large amount of material, more than just couple of pieces of substance. We have a huge amount of these, and we want to move them across this membrane all at once. And for them to sneak through the plasma membrane just passively, that would take way too long of a time. We want to make this move much, much, much quicker. So we are going to do active transport. We are going to spend energy, and we're going to move them all at once. That would be the first example of bulk transport. So what we do in bulk transport, the first example, we take all of these and move them across all at once. That's the first example of bulk transport. The second example of bulk transport is when we have something that we want to move across, but what we want to move across is physically so big that it cannot sneak through this plasma membrane, and it's also too big to travel through a protein. It's a large particle, so it's not going to be able to use either of the processes that we've seen before. So again, for transporting a large material across the membrane, we're going to need to use bulk transport. And how bulk transport works is that the membrane kind of encircles. So membrane is normally here, but it slightly encircles this material that we want to transport and allows it in a vesicle to pass to the other side of the cell. And once it's on the other side, that vesicle can then open up and we can release these substances there. So that's a quicker way to transport large amounts of materials. Or again, the same concept, and I think that the lecture video had a much nicer drawing than what I'm going to be able to do in this short amount of time. But again, if we have a large particle, it gets taken inside a vesicle. The membrane here, cell membrane, just almost opens up, encircles this large molecule, allows this vesicle to fuse into the cell membrane and cross to the other side, and then it opens once it has crossed over. And that's how we transport a large molecule across the membrane. So the two examples of those that we had when we had to move a lot of material at once, or when the material is very large. It's too large to pass through the traditional means that we've seen, either through the plasma membrane itself or by using a protein. And we had two types of bulk transport. Endocytosis was into the cell, whereas exocytosis was out from the cell. So the direction where we're transporting mattered as well. So I think that completes our review of the material for the exam 2. If you remember, I normally provide the Planck study guide for you. That's on your Blackboard shell, and all these fillings that we've done to this study guide are listed on this video, so it might be worthwhile to watch it. It's up to you if you feel that helps you. I don't normally post this completed version of a study guide anywhere, but I hope that you have found it helpful, and if you have any questions at all, do feel free to give me a shout out, but I do really recommend that you refer back to the full lecture videos. They really explain all of the concepts. These study guides are simply supposed to highlight the key points. However, you do remember that usually in my exams, pretty much every question is from the study guide. There might be a little bit adapted from the study guide. There might be need to combine elements of the study guide, but there's no curveballs. There's no new questions, nothing that we wouldn't have covered already earlier on. So like I said, this review session was divided in 2 parts because my recording ran out of the time during the first one, and I hope that you found it helpful, and like I said, refer back to the full lecture videos if you have any questions. I'm gonna wrap it up here. This completes our study guide for the exam too. Bye.